Yes, now live stream.
Yes, I'm launching it. So I put it on mute, but yep, there we are. Okay. I think so. We don't have Bala, do we? So I'm gonna admit everyone in and mute everyone, so then you can start in a minute. So.
그치.
Sure, you may want to start.
Good morning, good afternoon, and good evening, everyone. We have an IJMF Spotlight Seminar now. Today's speaker is from Korea. Let me introduce the speaker. The speaker is Professor Hyungmin Park, Seoul National University. Professor Hyungmin Park received his BS and PhD degrees from the Department of Mechanical and Aerospace Engineering at Seoul National University, Korea in 2000 and 2010, respectively. In 2013, he joined the Department of Mechanical and Aerospace Engineering, Seoul National University, as an assistant professor, and currently serves as a professor. Actually, he just became a full professor last month, so March 2022. So he's a new full professor in Seoul National University. Before joining the Seoul National University, he worked at the Hyundai Heavy Industry and also conducted research as a postdoctoral researcher at UCLA and USA. Professor Park's major research interest covers the fundamental and applied studies on the mass phase laws, flaws over the functional wettability control surfaces, and fluid structure interaction, mostly based on the experimental approaches. Today, he's going to talk about the from fundamental to practical aspects of bubble-induced agitation. So, Professor Park, please start.
Okay, thank you for the kind introduction, Professor Shudakaki. And also, I really thank you for all the editorial board members of IJMF for inviting me for this wonderful online classes. So let me share my screen for the presentation. So as introduced, I'm going to talk about the fundamental and practical aspect of the bubbly flow that we have actually investigated for past about 10 years. So before we start, let me briefly introduce what we are doing in our lab in SNU. So here, the sum of the movies and snapshot actually shows some examples of our major research work. So as you can see, we are mostly interested in various kinds of the multi-phase flow, including the bubbly flow or particle-laden flow, or even the movement of the sessile drumlets, as you can see at the bottom. And also we are interested in some kind of the fluid structure interaction problem. Mostly you are doing experiments, but if necessary, we do some, we get the help from the numerical simulation. Okay, so today my talk will be about the gas liquid two-phase flow. As you already, many of you are familiar, when the gas bubbles are formed from the various regions as shown in these movies, and if they evolve in a liquid flow, it is quite well known that they can change the liquid properties such as the density, viscosity, or thermal conductivity, and so on. And also they are highly related to the transport phenomena of mass, momentum, and energy of the liquid flow. And sometimes they are the major source of the pressure drop and the mechanical damage as well. So therefore, it is quite a tricky problem because even in the same flow geometry, someone wants to use the bubbly flow or bubbles to enhance the performance of the system. But the others, on the other hand, want to detect and remove the same bubbles to avoid the degradation of their system. Okay, so in this talk, so I'm gonna first briefly discuss some fundamental nature of the bubble-induced flow that we have learned so far. And then I'm gonna introduce two of our recent efforts to use the bubbles as a tool of the flow control. So for example, one example is the heat transfer augmentation, and the second will be about the fluid mixing enhancement using bubbles. So let's start with the most simple problem. So this is the single bubble. So as some of you already know, when the bubble size is quite small, for example, if it is smaller than approximately 1 millimeter in diameter, for the case of the air and water, so its shape will be typically spherical. And as you see here, the wake structure behind the rising bubble will be standing wake. So as a result of that, the bubble will rise following a straight curve. But when the bubble size increases slightly, this is on the bubble size about 4 millimeter, and the wake vortices behind the bubble becomes unstable and it is separated. And depending on the sign of that vortex pair, actually the bubble follows the two-dimensional zigzag or three-dimensional spiral path. And in this case, the bubble shape will be typically ellipsoidal. And this is typically called as the path instability. This is the very well-known phenomenon. So as is shown individually, the wake structure behind the single bubble is the origin of the path instability. But as you can see the movie on the right-hand side, which is what we measured at the bubbly flow in a vertical pipe, when the individual wake structures, they are have some collective effect, and we know that it is the source of the bubble-induced entrainment or bubble-induced agitation, so-called pseudo-turbulence. So let's try to increase the number of bubbles. So as you see in the picture on the left, this is the bubble chain problem. So here we experimentally investigate how the liquid flow is induced by the bubble chain. So we are using just a single nozzle, and then we change the bubble generation frequency shown here as of the FB. And as you see in this graph, starting from the single bubble case, we increase the bubble generation frequency. As you can see, this shows the collected the bubble trajectory. So as the bubble generation frequency increases, the organized rising path of the in-chain bubbles is strongly disrupted. When you look at the instantaneous vertical structures generated by these chain bubbles, as highlighted here, you can see that the vertically slanted lip-like flow structures are generated from each bubble consisting of a single bubble chain flow. But this is the instantaneous vertical structure. But when we move on to the time averaged flow structures, unlike the previous lip-like structure, we can measure the very famous jet velocity profile, as you can see here. So on the right, you can see our measurement. Here, the symbols are the measured vertical liquid velocity, which shows a very similar trend with the typical single-page jet flow. So our focus was to model how we can model the liquid flow velocity induced by this bubble chain. So here we used two contributions. One is the W1, which is the flow induced by the bubbles at the position of our interest, which means it is the contribution by the trailing bubble. And the second velocity component is the evolution or spreading to the lateral direction of the flow induced by the leading bubble. That means we are considering two contributions from the trailing bubble and the leading bubble. And then as a result of that, here the solid lines with blue color is our modeled data for the vertical liquid velocity. And as depending on the bubble generation frequency, we showed that our model reasonably predicts the measured liquid vertical velocity. So when we have more number of bubbles in your bubbly flow, our concern is about the scale-wise analysis. That means we are interested in how the interaction between the scale of the bubble-induced flow and existing scales occurs. So this snapshot shows the turbulent bubbly pipe flow measured at the Reynolds number of about 5,000, and the void fraction was about 1.8%. So to do some scale-wise analysis, we using the multi-scale wavelet decomposition, we decompose this instantaneous flow field into multiple flow fields depending on their length scales. Here, WL means the wavelet level, so the WL1 is the largest scale, and WL4 means the smallest scale. So the number of the decomposed scales is determined by the resolution of our measurement. Okay, so if you compare this decomposed structure and the original instantaneous structure, we can judge that the wave level 2 is quite similar to the original one, right? So then when we wanted to quantify what actually this length scale corresponds to this wavelet level. So using the calculating the autocorrelation function for each velocity field, we compared the length scale corresponding to each wavelet level to the existing scales of the turbulent flow. That means from geometric scale, which is the largest one, to the dissipation scale, which is the smallest one. And then we found that this wave level 2 corresponds to the integral scale of the existing turbulent pipe flow, which is the most energizing scale. So this here we can imagine that then in this configuration, the bubble-induced flow will try to energize the single-phase flow. So that means as a result of that, when you measure the Reynolds stress for this problem, here these black circles are the single-phase flow, and this green square is for the bubbly flow with this void fraction. And then you can see that turbulence is strongly enhanced near the wall due to these bubbles at this condition. But with this in your mind, when we increase the Reynolds number to 44,000 and then keep the void fraction of the bubbles in a similar level, and then we do the same analysis using the multi-scale wavelet decomposition. And then compared to the previous one, here we can see that now slightly smaller scales corresponding to the wavelet level of 3 or 4, or combination of these two can represent the original instantaneous flow. That means now our the bubble-induced scale of the bubble-induced flow now is moves to more to the dissipation scale. So as a result of that, when you see the Reynolds stress distribution, so now near the wall, we can see that even you introduce the bubbles with the same amount of bubbles, as the single phase flow Reynolds number increases, you have actually the reduction of the turbulence near the slight reduction of the turbulence at the wall. So that means actually the interaction between or comparison of the scales between the bubble-induced flow or bubble-induced agitation or some existing flow scale is very important to understand what you will do with your bubbles, right? So when your void fraction increases much higher, like the bubble plume, as you see here, our focus is how much you can increase or enhance the momentum of the liquid by adding the bubbles. So I'm going to talk about the details of this problem later when I talk about the mixing problem. But here, as you see, you can see in this graph here is MT, which we call total liquid momentum contributed by this the time average liquid velocity and the fluctuating liquid velocity components, and it is nicely scaled with another parameter I we call interfacial momentum transfer, and that interfacial momentum transfer is determined by alpha, which is the void fraction, and UC is the liquid velocity, and here VR is the relative bubble velocity. So again, here it means that the relative scale between gas phase and liquid phase matters to determine this the momentum augmentation by this by using the bubbles. So the similar approach actually can be used to model the turbulent stress or Reynolds stress induced by bubbles. So this is the problem of the uniform bubble swarm disturbed by this kind of some obstacle. We use the circular cylinder. So we have a uniform bubble swarm, but when you introduce the flow with this kind of obstacle that is disturbed, that means you intentionally introduce the spatial gradient of the bubble or liquid statistics, right? So then, as you can see, I'm not going to talk about the details how we got this, but just by modeling the individual bubble wake, we were able to model this Reynolds stress in terms of the liquid velocity gradient, relative bubble velocity gradient, and the gradient of the void fraction. So as you can see, for this problem, the measured Reynolds stress and the modeled Reynolds stress using this long equation actually shows a great argument to each other. So again, here we can see that this relative bubble velocity and its gradient is very important to understand the turbulent nature of the bubble-induced agitation. So based on all of this fundamental knowledge that we have obtained, then we wondered how we can use these nature or properties of bubble-induced flow as a kind of flow control strategy. So one thing is the bubble-induced mass momentum flux. It can be used to transport of something, and you can use bubbles to enhance the mixing efficiency, or like the bubble curtain technology, you can use the bubbles as a kind of screening method. If you are interested in the bubble-induced fluctuation, you can apply bubbles to make a direct reduction. Also, you can do another different type of mixing or heat transfer. Also, if you want to separate some species or materials, you can use bubbles. And also, indeed, there are many more you can imagine with your bubbles if you use the nature of the bubble-induced flow or agitation. So here I'm going to talk about first about the single bubble induced heat transfer, and actually this is about cooling effect. So as I showed in the first slide, for the single bubble with a sufficiently large size, due to the wake instability, it rise following a oscillating path like zigzag or spiral. So, but when the same bubble lies near the solid wall like this, depending on the distance between the wall and the bubble, which is shown here, S is the distance and REQ is the equivalent radius of the bubble. And then the number is their ratio. So as you increase the distance between the bubble and the wall from left to right, when the distance is quite small, you can see that the rising bubble periodically bounces off the wall and then rises, and then its periodic bouncing transition to non-periodic bouncing, and that is highlighted with the red colored box. But when you increase the distance further, and that the bubble dynamics changes to irregular oscillation without collisions. So that is what we have measured, right? And this is also related to the significant modification of the molecular structure behind the solid wall. So on the left is the case without the wall, and actually I have shown this one earlier. So this is the side view. You can see the nice separation of the vortex pairs behind the zigzagging bubble, and this is what you see from the bottom to top of the bubble, and this is the isometric view. But when you locate the wall near this rising bubble, you can see that as the bubble bounces up on the wall and moves away, it tends to leave a lot of strong molecular structure on the wall, as you can see here. So then our idea was how we can use this remaining molecular structure or strong fluid energy as a tool to enhance the heat transfer. That was our main idea. So to confirm that idea, we did some experiments with a tank with tap water, as shown here. The temperature of the water was maintained about 15 degrees Celsius. And on the one side of this tank, we installed a heated wall. That means we applied the constant heat flux to increase the temperature of the wall up to 20 degrees Celsius. And then by introducing a single bubble near the wall, and then we simultaneously measure the flow structure and the wall temperature using the two-phase PIV and the IR camera, respectively. Okay, so for the bubble, we consider two kinds of the bubbles. So one is the bubble with following the zigzagging trajectory. So that means it is slightly larger one. And then we change the distance between the heated wall, and the bubble, which is shown here. And then For the second case, we also considered a little bit smaller bubble, which will follow a straight path. And also we considered two different distance between the wall and the bubble for this smaller one. Okay, so this is the representative results to confirm that whether how much to see that how much heat transfer enhancement, if it can be obtained, occurs with a single bubble. So this movie will show the particle structure of the rising bubble on the right, and on the left we are looking at the Nusselt number variation around the vertical direction of the wall. Here the Nusselt number was normalized by the Nusselt number of the case without the bubble. Okay, so as you can see, as the wake structure separated from the bubble attached or interact on the wall, you can see that locally there, the Nusselt number enhances significantly, and that can be sustained even the bubbles already gone away, right? So then here we confirm that, okay, so even with a very small single bubble, it is possible to achieve the significant enhancement of the heat transfer. So then, as you saw, when the particle structure actually attacked to the wall, actually we got the heat transfer enhancement. So the key was how this particle structure from the bubble wake interact with the wall. So we try to track each particle structure emanating from the bubble, and here each symbol, triangle, circles, and squares will denote each vortex pair, and then their trajectory is shown for each bubble wall distance as star from the smallest one to largest one. And on the symbols, we have different colors from blue to red, which will show the relative magnitude of the horizontal velocity. Okay, so as you can see, depending on the distance between the bubble on the wall, different number of wake vortices actually goes to the wall, and their vertical range of the interaction is different, right? And you can see that for this S star of 2.4, we have four wake vortices actually reaches to the wall, and the vertical range is the largest. But for the case of this 9.7, actually this, even before attaching to the wall, each vertical structure actually they are dissipated away, so they don't have a chance to interact with the wall. Okay, so with this in your mind, so we are looking at the YZ plane of the heated wall. So we are looking at the heated wall itself, and here I'm going to play the movies which shows the temporal variation of the Nusselt number. Here, when you see the red colors, it means you have a heat transfer enhancement. That means that part is cooled down with the bubble-induced flow. So this is the 0.5, which is the smallest distance between bubble and the wall, and you see this 1.5, 2.4, 3.2, and this is 4.5, 5, and oops. And this is 6. So you can see that it was highly correlated what we have shown in previous slide. So depending on the number of the vortices, you can see the peak of the Nusselt number, they are correlated to each other. So let's look at the details for some specific cases. So this is this on the top, we show the temporal variation of the Nusselt number contour, and on the bottom, we have the vertical structure at the same instant. And here we have some numbers on the top. Here G, B star means the vertical position of the bubble at that corresponding instant, right? So this is the case when S star is about 0.5, means that our rising bubble actually first have a physical contact with the wall and then bounces away. So as you can see here, when the bubble attack to the wall, we have a slight increase of the Nusselt number, and that is the green color, right? And then this bouncing bubble moves away. The vertical structure from the bubble actually interacts with the wall, and then we have a red color. That means we have more enhancement of the Nusselt number. And as the bubble moves away, the region of the Nusselt number enhancement is elongated vertically, and they tend to move along in the vertical direction as well. So this is the case of S star of 2.4, and then you can see that we have 4 different peak of the Nusselt number, which will correspond to the 4 different wake vortices that actually interact with the wall. And then here, as I highlighted these red boxes, and you can see that similarly, as I have shown in previous slide, this bubble-induced wake actually tends to stay on the wall for a longer time than other cases. That means it has more chance to have an effect on the wall temperature from the bubble-induced flow. Okay, so this is the temporal variation of the delta G star, means the vertical range of the Nusselt number enhancement by the single bubble. So here, red color means the smallest wall bubble distance. Then from red color, when you increase the distance from the bubble to the wall to 2.4, you have more vertical range. But after that, this vertical range seems to goes down as you increase the bubble wall distance further. Okay, and that is consistent with what you have observed so far. Interestingly, for the horizontal range, so now we are looking at the YG plane of the heated wall. Irrespective of the bubble wall distance, the horizontal range of the Nusselt number enhancement due to by single bubble is almost constant with as of the 3 times of the bubble size. That is what we have measured. So then question is, then I think I have already given the answers, and we wanted to find out the optimal distance between the bubble and the wall to maximize the Nusselt number enhancement. So we integrated this Nusselt number variation on the heated wall as a and also along the time duration, and this is the result. So this is the integration of the Nusselt number augmentation as a function of the bubble wall distance. And you can see that it first starts to increase and goes down, and the optimal value for the distance was about 2.5 that we have seen consistently. And we have some questions. Then how about the bubble with straight path? So we also consider 2 different cases of the bouncing bubble when the distance is quite small, and then non-bouncing bubble when distance is slightly larger than the first one. Also, we have simultaneously measured the flow structure and the Nusselt number variation. And as you see, as the bubble goes up, actually the Nusselt number fluctuates within the uncertainty range. So that means we don't have any significant effect from the bubble. So we wanted to find out why this happens. So we estimated the thermal boundary layer on the heated wall, and then we found out that for the zigzagging bubble, actually the bubble-induced flow tends to bring the cold water from the bulk to the wall. That means it disturbs the thermal boundary layer. But for the small bubbles, actually it just moves inside of the thermal boundary layer, so it does not disturb any of it. So that means the main mechanism for the heat transfer is entrainment of the colder bulk liquid into the wall by disrupting the thermal boundary layer is the main mechanism of the heat transfer. So let's talk about, I want to talk about the second problem of mixing enhancement by bubble plume. So before we go, I talk about the details. We found out that we are able to generate 2 different types of the bubble plume, which is, as you see here, it seems like quite organized. We call conventional bubble plume. And the second one is the turbulent bubble plume, as you see in the right-hand side movie. And then we found out this can be categorized by as a function of root number on the x-axis, which is the ratio between fluid momentum to the gravity flux, and the y-axis is the H is the tank size and D is the spuddle size, and their ratio. That means it means the fluid weight above the spuddle. So that means depending on their ratio, actually we found out that even we introduce the same amount of the gas from the spuddle, it is possible to have two different types of the bubble plume. So we wanted to find out which one is more efficient in mixing two different fluid. Okay, so to measure the bubbles, we used conventional shadow graph using two light source and two high-speed camera. To measure the bubble velocity, actually for this kind of problem, it is impossible to measure the bubble velocity with some conventional method like PTB or PIB, whatever. So we use the optical flow algorithm, which is actually the image intensity-based velocity measurement technique, which means it evaluates the velocity field based on the change of the light intensity, and it is not depending on the bubble itself. So it just divide the image into multiple windows like PIB, and then just try to quantify the intensity variation, right? So you can see that we confirm that the result is quite reasonable. So even with this higher void fraction problems, it is possible to get the measurement data for the bubble velocity. And for the liquid phase, we use the typical LDA measurement. Okay, then, so as we have seen, the bubble plume, the major role of the bubble plume is to add momentum to the vertical direction. But as you saw in the movies, the lateral oscillation is also very severe. So to quantify this unsteady bubble plume kinematics, we define three things. One is precession, which means how your center of bubble plume is tilted against this average center. Second is mindering, which means where is your instantaneous center based on the tilted center. And the second is the bulge, which means how is your instantaneous width of the bubble plume compared to the time averaged one. Okay, and then we measure them using this kind of the image processing from the shadow graph data. So this is the result. So the first picture is the width of the bubble plume. So whether it is conventional bubble plume, which is the red color, or whether it is the turbulent bubble plume, which is the blue symbols, they are almost the same because we added the same amount of the gas. But the bulge, precession, and mindering, which means the unsteady kinematics of the bubble plume, as you can expect, the turbulent bubble plume has more unsteadiness along the lateral direction. Again, I want to emphasize that this bulge, precession, and mindering means the lateral oscillation, not the vertical oscillation. Okay, so from the LDA measurement, so this is the mean vertical velocity, and these two are the turbulent kinetic energy of the liquid phase. So when you compare these two, they look, the conventional one and turbulent one looks quite similar, but the turbulent one has a little bit narrower bubble plume width, right? In terms of the turbulent kinetic energy, TKE, you can see that clearly the turbulent bubble plume has the stronger turbulence, right? So as I mentioned, for this bubble plume problem, we wanted to know what parameter determines the momentum augmentation, and we wanted to relate them to the mixing enhancement parameter. So here we start with the time average two-phase Navier-Stokes equation for the liquid phase. So this is quite a conventional one. We have the convective term, pressure gradient, viscous stress, residual stress, gravity, and surface tension, and the last one is the interfacial momentum transfer. So we are going to apply this equation to our bubble plume problem, and we wanted to draw some scaling relation. So we had many assumptions, like the axis symmetry geometry from our plume. So the vertical velocity is much faster than the radial velocity, and the higher Reynolds number, higher Weber number, something like that. Then when you apply all of these assumptions to these above equations, actually you can simplify the equation quite significantly. So you get this. So simply you have the convective term and the pressure gradient, those two survive, and then also the interfacial momentum transfer survives, right? So you have this scaling relation. So here, from the convective terms, you get the contribution from the mean vertical velocity, fluctuating vertical velocity. From pressure gradient, you have the contribution from the radial fluctuating velocity. But now we have to deal with this interfacial momentum transfer. So for the interfacial momentum transfer, actually, there are a lot of different forces, but we decided that the drag force, additive mass, and the historic force, those three are the most dominant terms for our bubble plume problem. So their typical formulations are shown here, and we also applied some same scaling analysis to each force terms. Then as a result, we found out that this interfacial momentum transfer is scaled to this term, which is alpha is body fraction density, Lg is the some characteristic length scale of the bubble plume, Vr is the relative bubble velocity, Uc is the characteristic velocity of the liquid phase, which we use the centerline velocity of the bubble plume of the liquid phase. So combining this result and the result from the previous slide, you get this. This is what I have shown earlier in this the present talk. So on the left, we have the total liquid momentum parameter MT, we defined like that. That is scaled to this interfacial momentum transfer parameter, which is function of the alpha, Vr, and Uc. And this should be valid for the bubble plume. And I'm going to show the same graph that I have shown earlier. So as you can see here, each symbol was obtained for different type of the bubble plume, conventional bubble plume and turbulent bubble plume, and measured at different vertical position, and they all have very nice correlation each other. So the total liquid momentum on the vertical axis is determined by alpha and the velocities of both phases, which makes the parameter I. Okay. So we wanted to extend the knowledge that we obtained for that bubble plume to the mixing. So this is using the same tank. We keep almost everything same, but now we use two liquid. For the upper liquid, we use the tap water, and the bottom liquid, we use the sodium acetate solution, and then we control the density difference between the upper and lower liquid, and then we use color CC camera to, and also we intentionally dye the lower liquid as a blue color, and then to quantify the mixing. I'm going to talk about that later. And also, we used two color CC camera to measure the process of the mixing. And also we used the same amount of the gas bubbles that we have used before. Okay, first, we found out that depending on the density difference between the upper and lower liquid, we found that there are two different types of the mixing pattern. So when the density is relatively small, this movie shows that the lower liquid dragged by the bubble plume tends to circulate and falling down through the sidewall. It tends to circulate, right? But when the density ratio is quite large, because of the higher density, the dragged lower liquid just falls down filling down like that. So it is a little bit different. It shows a little bit different pattern depending on the density ratio, right? So here, this slide shows how we visualized and quantify the mixing process of these two different types of the mixing pattern. So since we use the color CCD camera, we can extract the blue channel values. So I want to remind you that we intentionally dyed the lower liquid with blue color. So the blue channel values can be extracted from the RGB image. And then using the time trace of that, actually we can determine the level of mixing. So for example, at this specific horizontal lateral position highlighted with this red dashed line, we measure the intensity of the blue channel, and then we add them around the as time goes on like this. So as you can see, initially before the bubble plume starts, we have clear interface between upper and lower liquid. So this is the falling type, and the bottom is the filling type, right? And then you can see that for falling and filling type, the direction of the upper liquid is different, right? And this starting point means that when we turn on our bubble plume, as after turn on, it starts to mix, and you can see that this is the very important parameter, and slope means the U low means the downward velocity of this interface between upper and lower liquid. That means when this U low is quite fast, that means the mixing occurs quite faster. So we have an idea that this velocity scale will determine the mixing time Tm is shown here. The mixing time Tm is the time taken for this standard deviation of this intensity goes below the 0.01, as you can see here. So for all different type of the bubble plume and the density difference, we quantify mixing time as I explained in previous slide. The graph is quite complex, but here I summarize two important things. The conventional bubble plume, which is the circle symbols, actually achieves the faster mixing than the turbulent bubble plume, which is the triangle symbols here. So the conventional one is more efficient in mixing. And that is the first one. Second is when the density difference becomes higher, the filling type mixing pattern is not that good because it achieves slower mixing. And that means the falling type is much better in enhancing the mixing of the two fluids. So that means for the present configuration, the mixing is governed first by the entrainment of the upper liquid by the bubble plume, and we have to make a circulation. And then that is the key to enhance the mixing. So as I said, the downward velocity of this interface, we call U low, determines the mixing irrespective of the mixing pattern. So we want to model this velocity scale. So when we highlight this area highlighted with this red box, this U low downward velocity of the interface will be determined by the crossplay between the momentum flux m dot and the gravity flux, as highlighted, noted by this orange colored arrow in the downward direction. So the ratio between this m dot and this gravity flux is nothing but the Fruit number, as I classified the bubble plume pattern using this Fruit number. But here we have the square of the UC, which is the velocity scale. And if you remember, for the interfacial momentum transfer I, we used these velocity scales with relative bubble velocity and UC. So when we change this bubble velocity scale with this one, we can define new Fruit number that will be responsible for the mixing efficiency. So we plotted the U low the downward velocity of the interface, which will be inversely proportional to the mixing time as a function of our Prudhomme number. And we can see that mixing time for both bubble plume, whether it is conventional or turbulent, they are collapsed into a single curve nicely, as you can see here. Okay, and this was I was the interfacial momentum transfer, and Prudhomme number we use the same velocity scale. Okay, but the interesting thing is the conventional one is better in terms of the mixing. So here, this is the last slide, and the question is, what determines the mixing? So actually, this is the momentum mass flow rate. This is the momentum flow rate. This is the precision and wind rate, right? So these two are shown already in previous slide, and here this blue symbol is the turbulent one. And as I said, turbulent one has more lateral oscillation. But in terms of the vertical mass flux or momentum flux, actually the conventional one shows us larger value. That means this it is understood that the strong radial motion or lateral oscillation weakens the mass flux or momentum flux, and it is not that good in achieving the faster fluid mixing. So that means you have to focus on the entrainment into the vertical direction. Okay, so in summary, so the fundamental understanding on the nature or property of the specific flow structure, which is mostly induced by the bubble wake, make it possible to use bubbles as a powerful method to achieve many kinds of engineering purposes. So I introduced two of them as of the heat transfer and the mixing. So the analytical investigation on those nature of the bubble wake or bubble induced flow are very critical in optimizing our approaches. So in the experimental approaches, more enhanced measurement techniques are required. As you can see in the bubble plume problem, it is a very chaotic problem. And to investigate the interaction between those pages in complex geometry. Okay, so I think this is the most important one. So I'm gonna thank you for all my graduate students for this wonderful work and my funders. And I'll be really happy to get any questions and comments. Thank you for your attention.
Thank you. Thank you very much for a very interesting talk. Okay, great. So any question or comments from the audience?
Sure, can I have a question?
Yes, sure. But please.
Dr. Park, it was a brilliant seminar. It was very informative. Thank you very much.
Thank you.
I have a question regarding the two kinds of plumes that you showed
Okay.
in the middle of the segment before you started talking about the mixing.
Mm-hmm.
There, the conventional one went straight up, and yeah, this one. But you were there was a plot where you regime map where yeah, this plot exactly.
Okay. Okay.
So my question is, I mean, these two plumes are distinctly different. In one case, you sort of had a homogeneous distribution.
Sure.
In the other one, you had sort of the instability and some clustering happening.
Sure.
Now, my question is, what is the role of fluid number in this one? So I wanted to understand why this value of about 0.1 to 0.5 demarcates these two regimes. So whether you have any thoughts on it, I was curious.
Okay, so that is very nice questions. So actually, yes, you are correct. So here the key is whether you have the conventional bubble plume or the turbulent one. our constant variable is actually we include the same amount of the gas from the bottom, right? And here, as you can see, the H is the size of tank, which is also fixed, but we change here D, which is the size of the sparger. So that means even everything is same, that means the hydrostatic pressure or the amount of the water above the sparger is same, and also the gas amount is same, but the sparger size determines how efficiently your injected gas actually it becomes as a bubble plume. So that's a kind of the H over D, as shown here, the fluid weight above the sparger as a kind of the hydrostatic pressure. So that is one thing. For the Prudhomme number, we actually gave the physical meaning to this Prudhomme number as shown here. It is the ratio between fluid momentum, which is given by the rising bubble plume, right? And at the same time, the bubble plume tends to drag the liquid to upward, right? And then at the same time, that direct liquid will go downward due to the gravity. So that is the counteracting effect, which is the gravity flux. So the Prudhomme number is the counterbalance between the fluid momentum induced by the bubble plume, and some other effect is try to go down due to the gravity and their relation. And that also those two actually determines which kind of the plume you can achieve, even with the same amount of the gas and water. So that means you can just, by controlling the size of this bubble puzzle, you can achieve that.
Thank you very much. I see other hands up, so I will let them. I have a few more questions, but let others ask. Thank you very much.
Okay. So we have a question from the Dr. Vivek Dua. So could you please unmute yourself? Yes.
Yes. Thank you very much. Thank you. Am I audible?
Sure.
Yeah, Professor Park, thank you very much for such an interesting talk. My question is that there are several applications in which we are interested in mixing achieved in such bubbly flows. And the overall mixing, as I understand, is the result of the convective flow that you have, also the recirculatory flow structures, plus the turbulent transport arising because of turbulence generated by bubbles, and maybe to complete it, it's also molecular diffusion. Now, with your work, is it possible to separate the contributions arising because of these different mechanisms somehow?
So, yeah, that is very nice questions, because when before I show this result to different people, and I always ask questions before I show the result of the mixing, which one would be efficient, the conventional one or turbulent one? And then almost many people answers that the turbulent one will be more efficient in mixing, right? But the result shows that in our problem, the conventional one is more efficient in mixing, right? I think, as I said, as shown here, we have a large tank like this, and the sparger is on the center size, right? So compared to the bubble plume width, actually we have a large tank. That's why in our configuration, as you said, the large scale circulation, that is entrainment by the bubble plume, is the key to determine the mixing. But what happens if you narrow your tank size to be comparable to the size of the bubble plume? Then actually this maybe turbulent bubble plume, we didn't check yet, but the turbulent will be more effective or should be comparable between these two, because at that configuration, the lateral oscillation will also play a very significant role in enhancing mixing, as you can imagine. But is it possible to separate the contribution? I think it will be a very tricky problem, because the measurement itself will be very tricky for this chaotic problem. So it will not that be easy to separately analyze the contribution from both.
Okay, thank you very much. And of course, there are more questions, but I think for that, I'll connect you offline through email and let I pass this to other speakers. Thank you very much. Thank you.
Okay, so Robert, your turn. Please.
Hi, thank you for your talk. It's great to finally put a face with the name. I've been following in the past few years, and it was a beautiful talk. Thank you very much. The one question that I have is regarding the heat transfer experiments, which I want to commend you for that, because these are, as you well know, these are terribly difficult experiments. And I was wondering if you can clarify, because, you know, if you want to measure the transfer of heat as a result of bubbles, I imagine that you're heating the wall, right?
Sure.
Yeah. So although you're heating the wall, you don't see the natural convection that arises from the heated wall. How do you prevent that from appearing in your images, or how do you handle that?
Yeah, that is very nice question, because I know you are doing the very good experiments, and if you are doing experiments with bubbles, many uncertainties can be involved. So actually, yes, this is the whole problem we actually tackled. So we have a heated wall here, right? And then we have bubbles rising in the water. And then also, since we are using the PIB measurement, actually we have to put the laser on the heated wall as well. That means laser will play as a source of the heat together, right? So that means we wanted to, eventually we have to find out this convection only due to the bubble induced flow. But as you can see on the right-hand side, we have a lot of different type of the heat transfer or heat migration passes. Like this, the first term is the generation, means the amount of the heat we added. And also through the conduction, that means the heat can be lost, and the lateral direction also heat can be moved. The capacitance will also the source of the loss. Radiation also can be a source of the loss. And also we have to add the heat from the laser. Actually, we modeled all of these things, and actually we calibrated this through multiple steps. And then finally, we were able to get the pure effect of the bubble-induced flow, and then we validated this value for different type of the geometry. Then actually the result you saw is the result of that validation. Yeah.
Thank you. It's a beautiful experiment. Thank you.
Okay.
Great. Great. Any other questions? We are increasing the number of the attendants. I'm afraid that some of the attendants might make mistake for the starting time.
Can I
Okay,
ask?
Bala, you have a yes, please. Bala, please.
Just one more comment to
Sure.
Dr. Park. You talk about mixing, but to me, this is a very, for bubble plume, this is probably natural, but in a general context of mixing, this is very special that you have a lower layer of fluid mixing with the upper layer of fluid. Sometimes we might want to mix even there may be a homogeneous fluid and mix as a whole. So
correct.
It's not very clear to me that which one is better at mixing. So when you talk about better at mixing, for this particular case where you have a lower layer and upper layer, then the conventional one is better mixing. So that's how I understand what you're saying, but I wanted to be careful that what I understood is correct.
Sure.
Because the sideways motion can be mixing the upper layer very well.
Right. Yeah, that's correct. Your understanding is perfectly correct, because as I said, in our specific configuration, we have a large tank compared to the bubble plume width. We have two initially separated liquid that eventually you want to mix. That is our definition of the problem. But as you said, if you have for example, you have some liquid and then you have some different species that you want to mix in a liquid, then maybe the turbulent fluctuation caused by the local velocity fluctuation will play more dominant role depending on the problem. Yes, correct. That your understanding is perfectly correct. Yes.
Thank you.
Welcome.
So Chao, do you have some question, please?
Hey, Professor Park. Thanks again for this beautiful talk. I really learned a lot. So, so my question is connected to the Roberto's question. Here for the national measurement, in fact, I had an identical question with Roberto. So I want to ask one more question. So this, for the national measurement, did you measure the local heat flux, or you measure the global heat flux for the equation number 2?
Equation number 2 means
on this slide. No, the second line. I think.
You mean this one?
No. The up one. The second line. The second line in the second line.
Oh.
For the national number. Yeah.
Oh, I
the
see.
blue
Nusselt number.
Yes.
So we measure Nusselt number is the function of space and time. So it is not the global Nusselt number. It is local Nusselt number on the heated world.
Yes.
So we measure.
Yes.
We use the IR camera to measure the world temperature variation. So that means
this I understand. Yes.
Yeah, as time goes on, we can measure the time variation on all the points on the heated world.
Yes, but that's the local temperature, right? But your your heat flux may also change.
Oh, we added the constant heat flux. We controlled. Yeah, we applied the constant heat flux. That's why we can measure define this Nusselt number. Yes.
Okay. This is clear.
Yeah, let's go back to the question. Yeah.
Thank you.
Yeah.
So I myself have lots of questions, but I just would like to one question. You have the results for the cylinder. Have you ever tried to measure the heat transfer for cylinder with bubbly flow?
Oh, yeah, I wanted to do, but actually so far I didn't meet other graduate students to wanted to tackle that problem. So yet clearly our next movement is to apply the heat to the circular cylinder and then to see how this bubbles for this problem. Yes, you mean this problem, right?
Yeah, more complicated, right?
Definitely, I want to apply heat to this circular cylinder to
very
measure
interesting to see.
how this bubble swarm affects the heat transfer of the liquid or the circular cylinder itself. So that will be clearly, yes, very interesting problem. Yeah, I want to do that. Yeah.
I would like to see the result. Thank you. Okay. So any other question or comments? No, if not, so the time has come. So thank you very much, Professor Park, for the very interesting